Hello and welcome. This is Dr. Schleich with another worked example. And this one reads, a particle of mass m and charge q is in a uniform electric field of strength E. The particle has acceleration a due to the field. Show that q over m is equal to a over e. Okay, so q over m, that's the charge to mass ratio. And here it's suggesting that it's equal to the acceleration per electric field strength. And we have to show that. All right, well, let's start with maybe the electric field is equal to the force per charge. All right. And we could probably say that because it's a uniform electric field, the object is going to experience uniform acceleration. So we've got force equal to mass times acceleration, Newton's second law. And then it's just a matter of, working through the alphabet soup there. So we don't have any force in this, but we do have mass and acceleration. So if we substitute that in, maybe it will just solve itself. E equals ma over q. You can kind of see we got mass to charge on this side. So what I'll do is divide each side by a. That's a q. And so now I've shown that the mass to charge is equal to the electric field to acceleration. So we just take the inverse of those, right? If m over q is e over a, then you do the old flip-flop, reciprocal, algebra, switcheroo there. There you go. Charge to mass equals a over e, right? So it's just a matter of substituting in ma for f and then, reorganizing it, sort of doing some algebraic manipulations. Pretty straightforward, 2 easy marks on that. The question goes on to read, the particle has a charge of 4e, where e is the elementary charge. The electric field strength is 3.5 by 10 to the 4 volts per meter. The acceleration of the particle is 1.5 by 10 to the 12 meters per second squared. Use the expression in A, it's that one, to show that the mass is 9u. Q over m equals a over e. So we've got q over m equals a over e, and we want to solve for the mass here. So I want to actually go back up to the way that I sort of had it up here. I'll switch it back over. M over q equals e over a, and then multiply both sides by q to get that the mass should be equal to the electric field strength times the charge divided by the acceleration. Let's clean this up a bit. So here's a good expression for the mass, and we'll just substitute everything in to give us the electric field strength. 3.5 by 10 to the 4 volts per meter. Now that's the same thing as a Newton per Coulomb, and it might be better to sort of leave it like with those units. So a volt per meter equivalent to Newton per Coulomb, force per charge. The charge, they give us 4e. All right, so 4 times e is 1.6 by 10 to the negative 19 coulombs. So their coulombs are going to cancel. And then the acceleration down here given 1.5 by 10 to the 12 meters per second squared. So we have a Newton per meter per second squared. You may recall that a Newton of force is a kilogram meter per second squared of acceleration. And so the meters per second squared would cancel. We'd just be left with kilograms of mass, if we consider the units there. All right, so 4 times 1.6 times 10 to the negative 19 is going to be what? 4.8 by 10 to the negative 19. .6 by 10 to the negative 19 times 4, 6.4 by 10 to the negative 19. I was thinking 3, come on, like 6.4 by 10 to the negative 19 coulombs would be the charge times 3.5 times 10 to the 4th newtons per coulomb electric field strength divided by now the acceleration 1.5 times 10 to the 12. It's a lot of acceleration. So you end up getting the mass in kilograms here when you're solving this, right? So we get the mass in kilograms. It wants to actually the mass in unified atomic mass units. And so let's just see what we get. When you solve this for mass in kilograms, you get 1.493, threes repeat, by 10 to the negative 26 kilograms. I'm going to put that value up here, 1.493 by 10 to the negative 26 kilograms. Now, a unified atomic mass unit is equal to 1.66 by 10 to the negative 27 kilograms. So we're hoping that when we divide this into that, we get a number that's very close to 9, right? They're suggesting that when we convert this out of kilograms to unified atomic mass units, we get 9. And what we actually get is 8.995. Right, so it all checks out when you actually, convert it, knowing that there's that many kilograms in a unified atomic mass unit. We find that it's very close to 9. In fact, when you round it, you get 9, like we would expect. Clear all that off. It says the particle is a nucleus. State the number of protons and the number of neutrons in the nucleus. All right, so now we're getting into some chapter 16 radioactivity, sorts of calculations. Before, this is really a chapter 8 electric field kind of a problem, but they fold in some ideas, All right, so we got some clues about this. Now, they never tell us really the particle has a charge of 4e. It would be nice as a positive 4e, right? So if there are 9 unified atomic mass units, but the charge is positive 4 elementary charges, I think that's all the clues that we need in order to deduce this. Does anybody know what the answer is? Each proton has a charge of positive 1e. And if the particle has a charge of 4e, then we could kind of assume that they're all from the protons, right? 4 protons. If it's got 9 mass units, 4 of them are protons, 5 of them got to be neutrons. 5 plus 4 is 9, right? So it's, once you have the concepts in mind, the mathematics is very straightforward. So only a mark for that. Almost a freebie. The second nucleus, that is an isotope of the nucleus in C, is in the same uniform electric field. State and explain whether the electric field produces for the 2 nuclei the same magnitudes of force and acceleration. So if it's an isotope, then it has the same number of protons. So it has the same charge. In other words, it's got 4 protons. But it's going to have a different number of neutrons. And so what does that mean? It's going to be more inert. It has more mass, but it doesn't have any more charge. So the ideas that we need to connect here are that an electric field is the force per unit charge. Because the isotope has no more charge, it's not going to experience any greater force. The force is going to be the same. Okay? State and explain whether the field produces for the 2 nuclei the same magnitudes of force, and we'd say here the statement would be the same magnitude of force. In the explanation, always remember to and explain. If it says state and explain, don't just give the statement. Same magnitude of force because the charge is the same, right? So same charge, 4 protons, 4 elementary charges means it's going to experience the same force. But the added mass or less mass, right? We don't know if this is an isotope of, something with 4 protons is beryllium. So we don't know if this beryllium isotope is light beryllium, right? It's got 1 less neutron or it's got 1 more neutron. It could be heavy or light beryllium. But in any case, it doesn't ask us, to say, it just says to compare it, right? Is it going to be the same magnitude? Well, no, it's not going to be the same acceleration. So we have to keep in mind F equals ma. This is the same. But because the mass is going to be different, right? Like what is an isotope? It's something that's either heavier or lighter because there's a different number of neutrons. So instead of this being, a particle, the second nucleus isn't 9U, it's either 8U or 10U, or there might be even more neutrons than that, right? It could be really heavy beryllium. But if it's got 4 protons, it is beryllium. That's what makes it an isotope. It's an isotope of the same element, okay? Same number of protons. So whether it's lighter or heavier, there's going to be more or less inertia and therefore a different acceleration. All right, so the statement would be, different acceleration, or the acceleration is not the same. And the and explain is because the mass is different, right? Because there's a different amount of inertia. So if it's heavier, it's going to accelerate less. If it's lighter, it's going to accelerate more. That's just anchoring your thoughts to arguably the most important equation in this level of physics, perhaps all of physics, Newton's second law. If you disagree with that, leave it down in the comments below. We'll have an argument. And that's the final, the 7 marks there. So you can see that the next question here, question 6, we're getting into defining the Coulomb, which we'll deal with next time.